Hello, everyone. My name is Pedram Sadeghian. I'm presenting on behalf of my PhD student, Alireza Sadat Hosseini. The topic of presentation is an effective simple fixture for testing GFRP rebars in compression. So I'm going to have a quick introduction, literature review, the experimental work that we have done, result discussion, a quick statistical analysis, and conclusion. So we know about FRPs. We are using it because of their corrosion resistance, so I don't bother you with this general information. The main topic is that right now in ACI 441R and the new ACI code, the contribution of GFRPs in compression kind of neglected. It has been replaced with concrete. So we say that in compression, you just put concrete there in compression. So that's the approach. This approach, I think it needs to be modified. It's too aggressive, and I'm going to show you the test result that we have. Just to give you a background, I'm from Canada. Canadian code right now, they started probably 4 or 5 years ago. They are allowing up to a strain of 0.002. So contribution of FRPs in compression up to that level is considered by the bridge code. And there is another code, S806, which is the building code in Canada, and they are considering 0.002 as well. But even, I think 0.002 is conservative. So, but at least in ACI, we can match, the Canadian version. So that's the story and the problem that we are going to solve. Just a quick, literature review. Multiple people have tried to test FRP bars in compression. Starting 1991, Brahim and Shalal and Dietz et al. So, for example, this did like this setup. Of course, because the FRPs are susceptible for local compression failure, so the end needs to be strengthened. So that's the approach with this. But the other people like Khan, they try to use just bare FRP, like ASTM for all FRP composites, and we are going to show that one underpredict hugely. And previously, my previous PhD student, Koramian, and my other student, Brandon Fillmore, we tried to have a cap at the top and keeping the aspect ratio of, free length over diameter of 2, and we got good results. But again, always there was some compression, a localized compression, I believe kind of premature failure in the cap area. So with the new fixture, we think that we are solving majority of it. So just another background is that there is no ASTM standard test for testing round FRP bars. That's the reality. So we have this ASTM, just put the FRP in between. It's very general. It doesn't work. And there are a couple of other ASTMs, just gripping by shear, but it's good for flat. There is another one, CLC. It's a compression and shear. That's provide the end bearing and friction. Again, that's for flat. So we are using the CLC modifying for the round bar. That's the story that I'm talking about. So from columns point of view, multiple people have tested Brian Ben Macron, Tony Nani, and even my PhD student, Koramian, because a slender column. Reality is that GFRP bars in compression, they don't crush. They crush way after crushing of concrete. That's the reality, and we are too aggressive in terms of, our code. And so they crush. A lot of times, that crushing is induced by buckling between two ties. So we need to consider. So we have 3 sets of tests. Just the first one is the ASTM D695 to see how it works. Just putting the bare FRP bars between of two plates. We tested L over D, length over diameter of 2, 2.75, and 4, 5 for each one to see, how it works. And here is the summary of result. You see the compressive strength in MPa and compressive strength over tensile strength reported by manufacturer. And these are the ratio. And you see the average is around 44% of tensile strength. And the failure was obvious, initiated at the ends. And that's what we expected. But we wanted to just to show that this test method doesn't work. But even this one, it's 44%, it's not 0. So the second round was that we thought that, okay, what about, having a kind of clamping system at the end? We machined it in our labs. Just grab the ends. Hopefully we can avoid that local, crushing. And then I have a small video. Hopefully I can run it for you. And that's what's happening. And you saw a quick shift as well. First of all, we were able to avoid crushing at the ends successfully, but the shifting was not solved. And that's another problem. So we need to avoid that shift. So, here are the kind of test results based on this one. We use just the one set of L over D. We reached to a strength of 650 MPa. The tensile strength was around 1,000. So the capacity in compression over tension was 69%. So from 44% we reached to 69%. So now it's a kind of new test fixture that we machined in our labs with the help of our technicians. So the concept is similar to the idea of the end bearing and friction together that ASTM has for flat bars, but we are machining something for round bars. So it has a multiple component, but these red bars are they go inside of the hole and they prevent any lateral movement. And so it can accept different length over diameters, and the blue parts it can be replaced for different diameter of the bar. So we tested these bars provided by Portra. At the time of research, we used the number 5, number 6, number 8 bar. For each one, 3 grades, 46 GPa, 50, and 60 GPA. We call it grade 1, grade 2, grade 3. And we tested 5 for each case. And we kept, for this presentation, I'm presenting just length over diameter of 2 of the free length. So here's just a quick process that how these things, cutting with the a bandsaw, applying strain gauges. We did a couple of try and error. We realized that we need to kind of provide a little bit cushioning at the end, so we use duct tape, of course. Of course. So we use duct tape at the ends. We found it very, very useful. Of course, it has been tightened with the hand, wrenching system. We put steel bars at the end, so the FRP bar doesn't go all the way. It's from this point to this point. It has 2D, 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 and then a steel bar with the same diameter is there, so it can provide so things doesn't get we get uniform clamping force. And again, that was through some try and errors that we end up to this fixture. So this fixture, the clamping provide the clamping force, transferring the compression force through the shear, then to compression, and of course the end bearing is there as well. So all is made in house. So these are the kind of a big picture of one sample per each case, number 5, number 6, number 8, grade 1 to 3. And for majority of cases, we were able to have the the failure in the gauge length. We had a few that happened, inside as well. Here is the typical load versus a stroke. These little things are a little bit asleep. Strain gauges provided very, consistent slope, and sometimes strain gauges they go away. For example, so at 15,000 microstrain, and then we have the load. So their crosses axis shows the final point. And so that's the kind of output that we put two strain gauges and we averaged, but most of the time we had very consistent two strain gauges, very similar, literally. We also tested all tension tests provided by manufacturer, but we tested one of the bar, one of number 5 grade 2 in tension to ensure that we get the manufacturer reported values, and it was consistent with that. So these are the values provided by the manufacturer, including the ultimate strength, modulus, strain, including a standard deviation and coefficient of variation for 3 grades and the bars. So here are the results for each group. Number 5 bars, grade 1, grade 2, grade 3. Horizontal line shows the tensile strength reported by manufacturer, and these are the compression results. So you see that the compressive strength is very close to the tension. We are in the range of 90% to 100%. Sometimes even you could go a little bit higher than tensile strength. So that's the reality that we are getting now. So here is the grade 6 modulus of elasticity, very consistent. As you see, tensile compressive strength, in the range of 90 to 100% of tensile strength, and the last one is the bar number 8. So same pattern. So very consistent in terms of modulus and compressive strength. So this one shows the summary of all test results. This is the kind of failure that majority of time we saw in terms of the crushing of the bars, microbuckling of the fibers. This microbuckling has been a kind of things that has been in the literature, and everybody referring to that one, but it's not happening that early. And so here are all results. So I think F compression over tension in terms of percentage, we have the average of 86% in total. In terms of coefficient of variation, very little, 5%. But there are some cases we had 16%, but overall in average we have around 5% variation, which is very good. One other thing is that the modulus of elasticity in compression over tension is 97%. So really, to me, modulus of elasticity in compression is the same as tension. So we should end this thing that it's kind of it's over or guidelines and code. And in terms of tensile strength, 86%. But to be honest, we are not reaching that point at all. It's way after 0.003. Way after. I think that's almost there. We did a little bit comparative study with the other studies, D'Antonio, my former PhD student, Dr. Ben Mokrans, my other students, just to see how is the, relative to the previous studies. And here it shows this study. First, it's, in terms of compression over tension, it provides the highest. It shows the effectiveness of the test. It's around 90%. In terms of modulus, we are showing a little bit lower than what has been reported in the literature. You see, in the literature, a lot of times shows higher. Yeah, it's in tension you have the cracking of matrix, but in compression there are no cracking. So modulus sometimes could go a little bit higher. But one thing that's in terms of variation, we have the smallest variation and consistency. And here are some histograms showing the you know, the variation of what we have got in terms of modulus of elasticity and in terms of compressive strength. So these are us that shows very. So overall average ratio of compressive strength to tensile strength in this study is 86%. With that being said, I would like to conclude this presentation. So it's obvious that ASTM D695 is not appropriate for testing, GFRP bars. A new test method, Fixture, is needed for that one. So we developed a new test fixture. We got the concept for the flat FRPs and converted to compression. In terms of compressive strength, 80%. In terms of modulus of elasticity, 97% of tensile one. And of course, we should pay attention to the clamping. It's very crucial. So it needs to be, the too much could hurt. Little clamping could hurt as well. And we are going to, continue this study with more, bars, Borna is providing more bars. We are going to extend it to effect of L over D to see what's the other thing. So here are the references that we are doing. I would like to acknowledge Virad Putra for providing the material and sharing their database. Of course, the technician at Dalhousie University in Canada and my PhD student. Yeah, thank you so much.
We have some time for questions again.
Pete Renshaw, Pultron Composites, New Zealand. Have you looked at the relationship between the compressive strength and the interlaminar shear strength? Because looking at this, it seems that it lets go by splitting, which is obviously a function of interlaminar shear.
We have not. I would say ASTM D695, because there is no clamping, that's splitting was very obvious, and that's our judgment that we went through, providing some clamping, but we have not studied that.
Okay, yeah. Alan Manano, he used to be at Sherbrooke and he's moved to Australia. He's also doing quite a lot of... Are you working with Alan on this?
A little bit, and I'm aware of, his work as well, yeah.
Yeah, because he's hoping to introduce this into the Australian building code, so it'd be very interesting to work with him on this. Thank you.
Tommaso D'Antino from Politecnico di Milano. Thank you very much for your presentation. As you can imagine, I'm really interested in this topic. I'd like to have your comments on a couple of topics. The first one, if I understood well, you used a free length which is 2 times the diameter of the bar. At the end, you made comparison with the results available from the literature. I was wondering if you compared results with the same ratio between the free length and the diameter.
So these ones that you see in the diagrams, that's all of them, they have same L over D.
Okay.
That's the thing. But there are other test data that, they have longer.
And that's 2 times the diameter?
These ones are all L over D of 2.
There's something wrong because at least my data are 4 times the diameter.
Yours, okay, I can
because in my experience, it plays a fundamental role, of course.
Okay,
if you increase the free length, you are completely changing the ratio between the compressive strength and the tensile strength. Also, did you try with different bars? Because in my experience, the type of bar, including the type of resin, the fiber volume fraction, and so on, play a very important role also in the setup, not only on the result. Because we tried something similar to what you proposed, and it didn't work for our bars. Especially, it did not work with bars with thermoplastic resin.
Okay.
So I was wondering if you tried something with the same or something else for different bars.
I agree with you. It needs to be expanded to different bars. Is providing we have already provided, so we are going to expand to that one. Length over diameter, to be honest, I think length over diameter, and it's about the spacing between ties, things. That's not, to me, it's not a material, aspect. It's a local buckling of the bars, and, you space the ties or a spiral to avoid that. So I'm leaning toward, just keeping the length over diameter to 2. This is kind of, everybody, it seems, agree that's kind of the most realistic one that we can do. It's not too short, it's not too long, but that's the other parameter that,
Okay,
yeah.
Thank you very much.
Akram Jodari, South Dakota State University. Interesting stuff. Thank you very much for your contribution. I know you have a lot of work on this. So one of the first graphs or the tests you did showed that eccentricity. And I think that might be the reason for the conservative ACI and CSA approach, because in reality, when we have columns, we do not have a perfect, pure axial compression, right? So there is always going to be, even like if you design it as pure axial, you're going to end up with 5% of eccentricity. So that will introduce bending in addition to the axial compression. So was that a factor, or maybe are you looking into that in the future?
In fact, that was the reason that we developed this fixture, to ensure that, there is no eccentricity. Things are aligned. So we are testing the real material property. But in reality, so always we have tolerances, and of course, always in column design there are accidental eccentricities that are considered somewhere else. But I believe that we need to focus on material property first, make it straight, and then, of course, considering other uncertainties into 5 factors and things. But that's very, very important.
Yeah, because I think the ultimate failure in reality in columns would be combined buckling, buckling and then compression.
We have seen it. Yeah, you're right.
Hey, how you doing? Anthony Noto with Simpson Strong Tie. Excellent presentation. One of the questions I had was, would the GFRP bars being cast in concrete reduce the failure modes, the localized failure modes of the GFRP bars, such as end splitting or, the splitting at the middle of the specimen? Is that the next step that you would do in your testing, seeing it actually confined in concrete specimens?
Not in this round, but even my PhD students testing slender columns these days, we see local buckling. But my main observation is that we reach to crushing of FRP, even like this, or see way after peak load. So we don't need to be that much conservative, to be honest.
Other questions?
Faisal Mukhtar from KPPM. Have you wondered whether St. Vernon's principle would affect your local material behavior, given that the boundary condition is very close to the failure region? What can you comment about that?
Could you repeat? I had a hard
St. Vernon's principle. When you
that's because we have the 2D. It's 45 degrees. So half D is the top triangle, half D is the bottom triangle. So then you are left with 1D in the middle that we can assume that it's pure compression. That's the concept, for all cylinders that we do the aspect ratio of 2, and it seems has been accepted, but there are concerns as well.
Thank you.
Are there any other questions? I have one. So in ASTM, they'll be very interested in the duct tape. So what's your recommendation on duct tape? How many wraps? What color?
That's a good question. That's hopefully in the next round of the test, we can replace it with more appropriate way of things, but that was, kind of the try and error to, make it a little bit uniform, clamping pressure. So that worked for us, but I understand your point.
Yeah. Well, actually, in a semi-serious way. I mean, did you put a couple layers around, or was it just one, or?
More than one, definitely, but, as we have a journal paper in the pipeline, so, but I will ensure that it's clear there.
It would seem like maybe most of the force is coming from that steel plug on the end, right? Is that steel plug exerting axial force?
Yeah, definitely. It provides the axial force as well, but the clamping force is significant. How much? I don't know.
Okay.